Here is the lecture for class 13 for ME401, 501. It's a velocity analysis. This is really a dynamics review to get you back up to speed. So that's what we're going to cover today. As you might recall from dynamics, for velocity is the time rate change of position. And as a formal thing, we could have the time rate change of the position vector, where we have a position vector at one point at point P. At another point in time at point P prime, we will have a different position vector. That would be R prime. And in between there, we'd have delta R. That's the which is going to be the position vector between those 2 points in time. And as we get smaller and smaller increments of time, they're going to get close. These 2 points are going to get closer and closer. And what we're going to find is that position vector is going to be tangent to the path. And it's going to be per time, so that's delta R, delta t turns into dr dt, which is the velocity. And what we find, the real good thing to know about that is the velocity is tangent to the path, right? That's what we take, our big takeaway, and something we should always remember. Velocity is tangent to the path. In rectangular coordinates, the position vector is just I, j, and k in 3 dimensions. So if we take the time derivative of that position vector, we got x dot I, y dot j, and z dot k. So that's to be expected, and we could also replace that this would be, say, vx, right? That would be the value of the coefficient in the x direction of the velocity, and then vy, and then vz. We're going to pretty much stick with things that are in 2 dimensions, so we don't need to keep including the x the k all the time in the z direction. One important aspect that you might not recall is that polar coordinates. The same thing exists, except that the position vector can be defined by the radius and then a unit vector that is aligned with that radial position right there. We could also write that it has another vector that describes the angle, but really the position vector ER already defines the angle because it is aligned right here. You'll see that the ER already kind of defines where the position is because it's related to theta, right? It's already bent over. If we go from another point in time right here, we could see that the unit vector has actually changed orientation. So coming back here for the velocity, if we take the time rate change of this position vector, like is the definition of velocity, we will have to not only change the time rate change of this magnitude of r, but also right here, so that's dr dt, but we also have to account for the time rate change of the unit vector, because it does change with time, as we've just seen right here in these 2 points. What we'll find inevitably, no, that's not what we'll find inevitably. Down here is what we'll find inevitably. But up here, we will say, well, we'll call it dr dt. We'll call it r dot. That's the rate of change of the length of the position vector. And then we'll have that r times the time rate change, just the e r of the unit vector dotted, right? And so we need to find this. So what we could do is this is sort of a derivation or an explanation. We could superimpose these 2 unit vectors over each other, and we'll see that let's just highlight one of them. We'll see that ER right here, when it changes from ER to ER prime, it changes by delta ER. And what's interesting is you could see that it points, and by taking that change in position, in angle right there, that the new thing that's changing right here actually points basically in the E theta direction. Similarly, the E theta, when we take it and here's the original E theta, and then it goes into a new E theta. Putting those next to each other, we see that the difference between those actually points in the negative ER direction, which is an interesting outcome. So like if we're going to, this is just to reconfirm and to get cross off and check off all the different things mathematically. But what we could say from this, what we've just rationale up there, is that the ER delta theta will, when taking the time rate change, will become E theta. Right, so but that's the change with respect to angle. We really want up here with respect to time. So what we could do is we could multiply E theta, d theta dt times that right there. And I believe, by the way, I think I made this mistake already. This guy right here should be d theta right here, because that's the thing that we're dealing with. So that's the thing that should go right there. And then you can see that the theta, d thetas are going to cancel out from each other, right? That d theta is going to cancel out there. And so, will not cancel out. What's going to happen, what's going to happen is we can substitute this right here. We can substitute and put that back in there and say that d theta is equal to E theta, and then we could also say that this d theta dt is theta dot. So that's what we're left with. And if we plug it back in here, we'll see that eventually that's one version of the equation. If we want to instead take a look at VR, right, so the velocity in the radial direction, and we could substitute omega into there instead. So this is just writing it a different way. It's just a polar coordinates velocity review. And what we'll often find with linkages, right? We'll often find in our linkages that the radial position doesn't change, right? That VR is equal to 0. So when we end up with a velocity for our linkages, it's just going to be the radius times the angular velocity, and it's going to be pointed in the E theta direction, which ends up coming over to the side, right over there. So it's going to be perpendicular to the linkage. So now going back to rigid body kinematics, anytime that you have a rigid body, you could break it down into a combination of translation and rotation, which is best explained by this relative velocity vector relationship right here, where we say that the translation is going to be the motion of one of the points that we know. In this case, the way that this is written. And did I do this again? Yeah, I need to frickin' fix this, right? So this equation, what I've written up above, should really be the velocity of A is equal to the velocity of B, and this would be the velocity of A with respect to B. And I'm changing that because I want it to coincide with my three diagrams right here. What this says is that B is the translation, and that it's the one that we use as our reference, right? And that's going to correspond to this diagram, where I draw three diagrams. Here on the left is the velocity of the total velocity of this rigid body, as defined by two separate points on the thing. And then this one right here. So when we're writing the equation, the equation is actually written for this particular point right here. And one way of also looking at it is we say that B is perhaps a velocity we already know. So we will use B as the reference. So on this point that we're zooming in on, we'll place the reference onto there. And then in the third diagram, we will pin the reference, and then we'll see how it moves about that reference. So that is the velocity of A with respect to B, which we happen to know from what we just talked about in polar coordinates right here is going to be R times omega. right? So it's going to be perpendicular right here. So another way we could say it's going to be, did I say W? I meant omega. Omega crossed against the position vector is another way, but we could also say that the value right there, the absolute value, magnitude of this A with respect to B. So once again, all of these equations right here, I should have fixed them so that they would match up with the diagram. So I apologize for that in our notes. Right, it makes it all messy, but we want to fix all those. And then for something we care about are multiple links. For multiple links, we can extend this for each one, that we know that the velocities of each of the joints are going to be the same no matter whether you're looking at this joint link OA or link AB or BC, that at each of the points they're going to share the same velocity. So if you want to know the velocity of C, you need to get the velocity of O, which we could sometimes we'll assume that's stationary, but not necessarily. And then we get the velocity of, we're able to find the velocity of A by taking, and here we have a theta dot, but that's the same thing as omega crossed with R, and that's R with respect to O. You notice that position vector right here. And if it's a rigid link, this doesn't change with time, and because it's a rigid body. And the same thing here. So we could go from one linkage to the next linkage to the next linkage, and we could find the desired velocity. And that's sort of how we're applying this thing in mechanisms. Another topic or another method of applying velocity is to do the instantaneous center of rotation. And the idea there is that at any instant, there's this magical point floating off somewhere. It could be on the body, that it looks like the body at that instant is rotating, is in pure rotation about that spot right there. And so we call this the ICR, the instantaneous center of rotation, where, and we could use that as the reference, and since the ICR is 0, what we say is that we could find the velocity of A is going to be omega across the position vector of RA with respect to the ICR, which is going to be this line right here. So all we need to do is find that instantaneous center of rotation and find this length, find the omega, and we can find the velocity, and vice versa. So any combination of those things. And it's kind of nice that once we found that instantaneous center of rotation and we found the omega, then now we could find the velocity at any point on the body. And that's going to be relevant to us in mechanisms, that we want to try to find the velocities at different locations. So one aspect of this is that we're always going to, when we're going to try to find the ICR, let's see, we're going to try to find the ICR of something. I really should have done an example of the ICR, like drawn some kind of body right here, and then drawn some velocities on top of it, right? So if we have we have a point right here, and I'm going to really screw this thing up. I got to be careful. If I have a velocity right here and a velocity, I don't know. Maybe I should go back to this other one over. No, I'll try it here. I'm trying to be careful that I don't screw this thing up by picking weird values. Let's say that I have a velocity like that right there and a velocity like this right here. And I'll call this VA and VB. What I want to do in order to find that ICR is to draw lines that are perpendicular to right here and through the point that we're referencing, and then right in here draw it perpendicular to this point, and then that right there where they converge is the ICR. And you can see that it's going to have an omega, that we can find the angular velocity about that ICR by finding this distance, dividing this velocity A right here by this distance A with respect to ICR, and then we could find the velocity of B because we already know the omega that we just found. We could find this distance. We just multiply this distance. So we keep using this omega times A kind of idea from right up here, right? Which was again from right up here, right? So that's the relevance of trying to tie these things together, is that we want to find the velocity of a rigid body. It's just the angular velocity times the distance right there, and the velocity is going to be perpendicular. And the same deal with this ICR. And what we find actually is, like, if let's say that this guy is rotating right here, it is about a fixed point, so its velocity would be in that direction right there. And then if this thing is rotating in that direction right here, let's say we want to find this linkage right here, and we want to find the ICR of that. Well, let's just skip over to this other linkage and find its velocity. It's going to be along a line that's perpendicular to there. So if we draw the lines that are perpendicular to the velocity now, we always got to be careful that you'll see that those are actually going to be the ICR is actually going to be a point where those two lines drawn through these linkage meet. So it's going to have an omega of 3 is going to be in that direction. Down here is going to be omega 2. And so now you're going to see that this point has to be about the ICR is going to give us a V. Did we label this? This would be VB. And by the way, this is VA right here. So we can see that this thing has to rotate here with an omega 4, right? So we have omega 2, omega 3, and omega 4. And you can see them operating against each other. And then over here on the right, they're pointing out that you can have, if this thing was rotating right here, we have a velocity of whatever this, it's not really labeled what letter that thing is called, but we have a velocity there, and then what we're able to do is find out what the omega is going to be here. So this is the ICR for this piece at this instant in time. Remember, ICR, this thing can move with respect to time. This ICR, so it's an instant in time that it's going to be right there. I'm not going to use this thing, and it's out of the book, but it is an interesting concept that you can look at, and you can see where you're trying to figure out the placement of these. I won't go into it though. So anyway, those are the ICR. What's one good thing because a lot of times we want to know things about coupler curves, and so that the coupler curve right here, we could just draw, once we find the ICR, then we can find what the velocity at C is going to be based on that ICR up there. So here is a long example, and I'm going to do this in a separate video. And then I think I have some other examples that I'm going to run through, and these are relatively long examples, and I'm going to do them in a bunch of different methods, so that you could compare. And then we'll do a slider crank and a 4-bar mechanism. So this is a really long sequence there. I think maybe I've already done these, so let's see if I did or not. So I'm going to discard all this in the video.